Hello everyone, Shine is here. Today we are going to solve a problem of beam design where you have a L-shaped beam with the provided dimensions. So the beam has a cross section of 20 mm by 40 mm, and this is subjected to a number of external forces. So the question is, you want to find out the multi-stresses developing at point H. H is a tiny patch which is at the top surface of the beam 50 mm away from its base, which is fixed to the wall in a cantilever fashion. Okay, three external forces, 2.5 kilonewton, 0.5, 3 kilonewton. And the question is, first you want to find out how these external forces develop normal stress or shear stress at point H, and then all these stresses, normal and shear, you have to combine them using the Mohr circle to find out either the principal stresses or the maximum shear stress. So once you find the Mohr circle result, in this problem you want to use the principle of maximum shear stress to evaluate whether the beam would fail at point H, given that the yield stress of this material is 200 megapascal. So the first stage is you have to solve this problem statically to find out the internal forces at H. So like usual, you make a free body diagram, a section at point H, and once you find the forces transform at this point, so stresses, normal, shear are calculated and then combined together before you can use the maximum shear stress principle to make a judgment. So let's get started. The first thing, let's make a let's have a closer look at the problem. All right, so easiest way to make this free body diagram is once you make a section, before making the section, we want to transfer three external point loads to point H. And there are two principles you can use. First of all, we know that vectors are free to move along their line of action. So 3 kilonewton can be freely shifted along this line of action and brought right at the... So I'm going to make a section here, right? So if I want to bring that 3 kilonewton here, I can do this straightforward without any change to the loading situation. But when you want to bring 0.5 kilonewton to this point H, because you are moving that normal to the line of action, the line of action for 0.5 is this one, and the distance between that line of action and patch H, that is 150 millimeter. So if you bring or transfer that force to this point, you have to add a penalty to your free body diagram, and that penalty is 0.5 times 150, and that would be in a clockwise direction moment. So you bring 0.5 here and add a 0.5 times 150 in a clockwise direction about the z-axis. So this is the z-axis, this is y-axis, and that longitudinal is the x-axis. So transferring 3 kilonewton to that cross section is okay. So every vector can freely be slided through the line of action. But when you want to transfer 0.5 to here, you transfer it first and then add a penalty about the z-axis, which is 0.5 multiplied by 150. Next step, you want to transfer 2.5 here, and well, because this time again you are transferring a force normal to the line of action. The line of action for 2.5 is along the z-axis. If you want to transfer it here, that's normal to here. Shortest distance between this line of action and that patch is 150. So in this case, you bring 2.5 here, and then you add a rotation about y-axis in a positive y-axis rotation direction, and that the penalty moment to justify that transformation is 2.5 multiplied by 150 millimeter. So let's have a closer look at the numbers. So we just start calculating the penalties needed for shifting two forces. Here in my free body diagram, you see that 3 kilonewton was exerted right in the middle of plane passing through H. So the center of that area I labeled that as point O. 3 kilonewton here, and then as a result of moving 0.5 normal to the line of action parallel to the y direction, so the penalty is 75 newton meter about the z-axis. So you see here 75 newton the penalty, 0.5 here, 3 kilonewton here, and the last step is to transfer 2.5 to that plane. I bring 2.5 here, but I do need to add a penalty because the force was shifted normal to the line of axis, and that penalty is 2.5 times 15 millimeter. So that is a rotation about the y-axis. So let's label these forces to avoid the confusion. This half kilonewton labeled as Fy, the rotation which it calls mz because that's about the z-axis. 3 kilonewton is labeled as Fx, no penalty to shift it, and to transfer the 2.5 kilonewton you bring that right here, and then the penalty would be about the y-axis 375 newton meter. So now this free body diagram is complete. So now the next step, given that the rotation was labeled as my and the force was labeled as Fz, so how these internal forces produce a stress over this cross section? Well, first of all, in this beam we realize that either normal stress or shear stress is not constant, except the 3 kilonewton which is exerted in the middle of the beam. It won't cause any changes. So you would have, if I want to check point H, so due to that 3 kilonewton, you would have a uniform distribution of stresses like so. So that stress you easily can calculate by dividing 3 kilonewton by cross-sectional area. So this is the uniform stress. We call this sigma average x, and that sigma average x is the first step you calculate. So that is 3000 newton divided by the cross-sectional in millimeter. So this is just a hint for stress calculation. One tip is to keep the forces in newton and dimensions in millimeter. Then you would get stress calculated in megapascal, and that's what we did. So that normal force would result in 3.75 megapascal at point H, and everywhere else that's uniform as I showed here. It doesn't matter, point H is here and O is right in the middle, but this is a uniform distribution. Therefore the contribution of that force at point H is a stress compressive. All right, now we realize two other forces, 0.5, 2.5. These are shear forces, and they are resulting in a transverse and longitudinal shear stress distribution or disc cross section. So transverse or disc cross section, with 0.5 you would have a shear stress which starts from 0 at H and become maximum at O. And with 2.5 you would, this is based on a shear stress is equal to shear force multiplied by Q I T. V is the shear force, Q is the first moment of area about the neutral plane. In this case, the neutral plane for 0.5 is ZZ axis, but when you put the 2.5, the neutral plane would be YY. So if you are using that formula for 0.5 and 2.5, the very same formula would be interpreted in different. For example, T, when you are applying that along the y-axis, that's the thickness, is from here to here, that is 40 millimeter. But when you are applying 2.5, T is from here to there, which is only 20 millimeter. All right, the next thing is these moments, they would make a linear distribution of the stress from the top fiber plane to the bottom fiber plane, and at the neutral plane the normal bending stress becomes 0, it becomes maximum at H. 0 here changes the direction at the opposite side. So given that this direction, you would have expecting a maximum tensile normal stress developing at H, reducing to 0 and becoming to compressive, the same magnitude on the opposite side. When you rotate about that axis, about Y, the developed normal stress at H is 0. It's maximum at the side faces given that direction. But because we're combining the stresses at point H, due to that force, 0 normal stress develops at H. That's a good news. And right, so the rest is number crunching. First thing first, I have calculated second moment of area IZZ when the active bending is 75. Also YY second moment of area about the y-axis when the active bending is 375 Newton meter. Also, I have labeled the cross section using letters lowercase a, lowercase b. So when shear is exerted vertically, you are interested in Q, or the neutral plane passes through BB. When the shear force exerted along the Z, the neutral plane would be AA. So for that reason, we have calculated QAA and TAA, QBB, TBB. So these are the numbers. And like I said, we keep all the dimensions in millimeter, all forces in Newton, such that the calculated stress becomes megapascal. All right, next we just calculate stresses. Like I said, the 3 kilonewton would result in average stress distribution over the cross section, including point H. Due to the bending about the z-axis, you would have a normal stress maximum developing at H, which is just replacing the calculated number here. You would have 28.125 megapascal tensile at point H due to a bending about the z-axis. But given that this is tensile and the one that due to the average stress is compressive, the net normal stress at point H is the difference between these two. So that given in mind. Now, due to the bending about the y-axis, there will be only zero normal stress developing at H, because with bending about Y is the neutral plane with zero normal stress. And then due to shear force of Fy, because this is the free surface, H is located at the free surface, the transverse shear stress at here is the amount of the shear multiplied by Q divided by IT, and with Fy, because here Q becomes zero at point H, with ZZ being neutral plane, so no shear stress develops at H due to Fy. And finally, due to Fz, with Fz the neutral plane becomes AA or YY axis, and here you just put the numbers and get 4.687 megapascal developing at point H. So just to repeat, all the forces are in Newton, dimensions in millimeter, and that give you megapascal for shear stress. Now you find the net normal stress, which is tensile due to the bending, compressive due to uniform normal stress, and then you would have 24.375 megapascal in tension developing at point H. So here the problem wants you to use the Mohr circle. So Mohr circle can be used either to find the principal stresses, which are called sigma 1, sigma 2. That is a kind of a resultant between stresses in the orthogonal normal stresses with the shear stresses. But the problem is suggesting not to find the normal stresses, but maximum shear. So according to the Mohr circle, the maximum shear is the difference between sigma xy in a two-dimensional planar stress. So this is the formula we are using, and there is no sigma y, this is only sigma x. So you just substitute that numbers here together with the shearing transfer shear stress you found, and that would give you only 13 megapascal. So this 13 megapascal, the principle of failure by maximum shear is wherever the maximum shear is smaller than yield stress by 2, that is safe. If you get this one equal, that's a failure point. So here we check. So what you found as a maximum shear, that was only 13.06 megapascal, and the yield stress for this material is 200 megapascal. So because that developed stress due to the internal forces according to this theory is smaller than 100 pascal, you can conclude that there is no failure taking place at H. So I hope you find this demonstration useful, and thanks for watching the video. Take care. Bye for now.